If you want to find the value of the force on the point charge, we need to find a way to take Q, the arc, and break it up into small pieces. So your first order of business is to find a piece of the arc and label it dq. This is more something you draw and less something that you write down. So just pick a place on there. So although I walked around and only saw about 5 or 6 of you, the 5 or 6 I saw all did the same thing. They identified a piece of the charge and labeled it dq. I'm sorry, D uppercase Q. Great. That's where we're going to start. But now, look at where that piece of charge is. We treat it like a point charge. It's going to apply a force on lowercase q. And that force is going to be directed clearly along a radius. That way? Maybe that way. Away from dq. Now, your job is to find a way to identify where that piece of charge is using some variables that you create that can help you determine each piece of the charge. For example, I'd probably say that dq is a small bit of arc length long, say ds. And maybe it's located an arc length of s away from the x-axis. This is a way I can start this problem. I don't know that arc length is the way to go, but it's a way I could start this problem. Since it's a semicircle, I know how long the arc is going to be, right? And we know things about arc length because we've studied geometry before. If the whole thing has a circumference of 2 pi r, the whole arc is just pi r. So I'd say that on the top side, I'm going to go from 0 to pi halves r. Right? That's how I could identify each piece. That's a way to do it. It's got some problems, though. And let me tell you what those problems might be. You'll notice that force is pointed downwards, right? Does just stating an arc length help us with what this angle's going to be? I don't think so. And is that angle going to be important? I think it is, isn't it? In fact, I think that angle is probably going to play a crucial role in determining how much force is actually acting on Q. And why am I saying that? Well, I'm noticing some symmetry. Are you noticing the symmetry as well? With that symmetry, I notice that if there's an F directed downwards, based on the symmetry, there's probably another F that's going to be directed upwards at the same angle, which suggests to me that I'm not going to be interested in F, but I'm going to be interested in F along the x-axis. Wouldn't you guys agree? And based on my observation, and I hope your observation, there's probably an F along the x-axis that is something like that, which is going to be related to the angle theta. I'm just looking to the future of this problem, but it suggests to me that perhaps in the future of this problem, I might have to consider that F in the x direction is equal to F cosine theta. Now, I used to assume that when I did something like this, all the students also easily saw in their little mind why I chose cosine and not sine. Well, yesterday and the day before and last year, it's been kind of made clear to me that sometimes you guys need a little bit more time to rationalize why I would use one trig function versus another. So, can you see from the picture why I chose cosine? Or do you need more input to understand why cosine was chosen. I'd be honest here. You all are good? All right. So now, I don't know that I can use arc length. I think I need to use a way of defining where that charge is with something that has to do with the angle. Do you guys know how to express an arc length in terms of an angle? Is this a no, I don't? Because everybody in AP1 in mechanics was taught this by me last year. Yes?
Is it ds equals RD theta?
There we go. So there's two parts to this, but the part that was just expressed I think is great. ds, this is how big that piece of arc length would be equal to r d theta, as long as this d theta is measured in radians. That'd be just fine. That would give me the size of this piece. Now, I'm pretty sure we can point to every piece too, right? If I wanted to, I could replace S with just R theta. All good so far? All right. So, step one was to identify a piece. Step two was to come up with a geometry that would allow me to point to every piece. And in addition to that, make every piece something I can use in my Coulomb's law equation. I think we're close. Our last thing is to come up with how much charge dq has in terms of the information provided. This is about density. So this is where we make a ratio. Something like dq to ds equals, now we're going to try and take the entire amount of charge and divide by the entire length of the bar. So Q over what? What's the entire length of the bar? Pi r. Looks good. I put theta though, and I meant to put a Q. So let's not walk around with more mistakes than we need to. There we go. Are we doing okay now? Left side too. Mr. Shelton. That's the problem with having E&M so early in the morning. There. All right. Now, we've got our density. We've got a means of expressing dq. We have our geometry. We want to construct a Coulomb's law equation that could be summed to produce the total force. So over here, I'm going to start with just our basic form of that equation. A small piece of the total force is going to equal Q times dq times K over the separation distance squared. That's the basic formula. I want to add something to it, but this is just the basic Coulomb's law formula. The truth is, though, each piece of force, each contribution to the force, has to be scaled to take into account the direction along the y-axis. So I'm only concerned with the pieces of the force, the contributions to the force that are in the x direction. So I'll take my function here and scale it so that I'm only looking at the part of the force that's along the x direction. Now, all is well and good, except we now need to kind of put everything in terms of one integratable variable. one variable that changes to point out each one of our pieces of charge. And right now I've got R here, which I'm going to have to replace it with something else. I've got my dq here, which I'll have to replace with something else, and maybe even my theta here. These are all things that when one changes, the other ones might change. Now, this geometry poses a particularly interesting scenario. Do you all realize, just from looking at it, that every piece of charge is the same distance away from Q? So when I start looking at making replacements, I think the first thing I'm going to replace is the value for the separation distance, and it's not changing. It's just going to be capital R squared, the radius of the circle. My next job, of course, is to try and write dq in either terms of s or theta. But if I decide to put it in terms of s, I also have to put the cosine in terms of s. So I think it might be easier to put dq in terms of theta. What do you all think? So let's see if we can come up with a way to do that. I'm going to look over here for that, and potentially here as well. You guys see all that? So let's kind of combine those for a minute and see if we can come up with a dq replacement. First, dq equals q over pi r ds. I just solved this one for dq. Next, I'm going to do some substitution with ds. I'm subbing in r d theta for ds. It was nice of somebody to give us this. Do you guys know why this is true? How many of you have ever used a compass before to draw circles? Okay, so only a couple of you. You guys know what a compass looks like? If you're going to make a part of a circle and you're going to use a compass, isn't the first thing you do is you set the radius of the compass by pulling apart the needles? Do you guys know what I'm talking about? I have one in the cabinet. If you want me to pull one out so you can look at it, we could see one for real. Would that help you? Because the next thing you do is you just put the point down where the center of the circle is, and the pencil part makes the circle, right? Well, what if I didn't want to make a whole circle? I just want to make a small piece of a circle. I wouldn't go around the whole circle, which would be 2 pi radians. I'd go around a small part of a circle, a small bit of arc. And wouldn't that produce a small piece of arc? D theta is a small movement of angle. If I multiply that by r, I get a piece of an arc length. That's all it is. And it comes from also knowing that circumference, which is the entire length of a circle, is equal to r times the entire angle of a circle. Right? You guys know this part, right? So circumference is the entire length. ds is just a little piece of a length. 2 pi is the entire angle of a circle. D theta is a piece of an angle of a circle. That's where it comes from. It's no big deal. All good? Now understand where it comes from? And could teach it back to me, should I ask? Because that would be the true understanding. I mean, I put some compasses in all of your hands. I have the safety compasses. You know, the ones that you can't stab your friend with? They're not as fun as the old style ones that had that long dart that you could stab your friend with. Do you guys know the difference? When I was a kid, that's what we had in our class. You could just stab the kid next to you. Just out of fun, right? Because you're screwing around in the 6th grade or something. You wouldn't do it in high school. All right, I think I want to do some replacement. Is that okay with you guys? But I think I'm going to cancel those r's out first. So it looks like dq will be q over pi d theta. All right. So here we go. df in the x direction equals q over pi d theta k over r squared cosine theta. All right, we brought all the pieces together. I'm noticing right away r squared is a constant. K is a constant. Q is a constant. Pi is a constant. Q is a constant. Do you guys see all of those? That is our collection of constants. So I'm going to take my equation here, and I'm going to break it up and put the constants all out front, mashed together. And I'm going to take d theta, which is my integrating variable, move it all the way to the right. So I can build an integrand. And then once I've done that, I'm going to apply my integral symbol to both sides. I'm creating an integrand. Now, who's already had AB or BC? All right, so I have a small subset of you. You guys understand from completing a course in calculus that there is a certain amount of symbolism required to express an integral. Right? That's what you learned by finishing calculus. What I want all of you to understand is we're putting in this order because this order tells the mathematician something specific about what they must do. They're going to be taking the antiderivative of this function with respect to this variable, and then applying these limits, should there be limits. That's what it's expressing. It's a format. In the same way that anytime we try to express something with a format to somebody, we use a format that is reasonable. Topic, sentence, supporting sentences, closing sentence. Isn't that a format that you use to write a paragraph? This is a format that's used to communicate an idea to the mathematician on what must be done. But you, as a physicist who is trying to understand physics, needs to understand that we built a function here. That is how much force is applied from a single piece of charge. And that we know the only way to get the total force is to add it all up. So this process of transitioning from building an equation to conducting an integral is placing faith in calculus that the execution of this integral results in a sum. Now, you guys who have studied the fundamental theorem of calculus and have gone on to understand the basis for the integral, note that you practiced a lot, noting that it was a true sum by usually taking the function, drawing it out, and then showing that an integral was the area underneath that function, right? Did you guys who did calculus remember drawing in all the rectangles? Yeah. And then you got to advance and draw trapezoids instead of rectangles because they were better, right? And that slowly showed you that the integral process does do a sum. I'm not going to show you any of that. That's what calculus is for. Your calculus class has that surprise waiting for you. And I'm so excited for all of you to learn that. What you're going to have to do is learn to do that without having to know the basis, because we need that information from you sooner. Okay, so I will need you to learn how to integrate before you're going to be taught it in calculus. Now, you guys who came from mechanics, you got a taste of it. I will say, in this problem, if this were on a test, and just to be clear, this would not be the only thing they would ask on the test. But let's say that this was on the test, and this was worth 7 points out of 15. Getting to here would be 6 out of those 7 points. You guys remember that from mechanics too. It's not about executing the calculus that gets you the point. A lot of times they will even give you the answer, so you don't even have to execute the calculus. Getting to here is hard. This is what needs to be taught to you. And this has nothing to do with what you're going to learn in your calculus class. Does everybody understand that? So this process, and I hate to be beating this down so much. No one ever taught me how to do this either when I took physics. They just assumed that we could do it in our physics class. And no one taught me how to do it in calculus. They just assumed that you were learning it in your physics class. And I've sent a lot of kids to college, and they say the same things. They don't really learn how to build the integrand from physics. They are just assumed that they can do it, that they know what a sum is, and they know how to get the pieces there. So look at our textbooks. They've seldom really go down the road of what it takes to do this. So we're going to see every possible example of a summation in here. Every possible shape that could show up on the exam, we will practice once or twice. In your notes, you are building exemplars, because at the end of the day, there's only about 10 different ways this can be done. About 10. I know it sounds like a lot, but you've already learned 3. Right? You learned the 2 point masses. You learned the bar. You learned the bar, right? And what I didn't talk to you about the bar is that when we did the bar, we did it all positive, right? And we saw the analogy between that and if it was just 2 point masses, right? Did you see that analogy when we were doing it? Well, what if the bar had a positive side and a negative side? Do you realize it would be the same work that we did when we had a positive charge and a negative charge? So what I mean by that, in fact, you've seen 3. You've seen probably both versions of the bar that you could be given. You've now seen the arc of charge. Now, there's lots of different arcs of charge. I gave you a semicircle. A couple years ago, they gave one that wasn't a semicircle. It was a quarter of a circle. Is it really that different? No. Everything up until this point is exactly the same. Everything. The only thing that changes is the size of your bar. So this will be a little different, and my limits will be different. We will see every single one of them. I'll leave nothing to chance. However, I think we should go a little bit farther than we did yesterday, because I think we can with this one. If I was going to execute this integral, I would have to say where the first piece of charge is and where the second piece of charge is. Can we agree that based on it being a semicircle, the first piece of charge over here, we could say is negative pi over 2, and this would be positive pi over 2? Now, somebody in here who has had calculus would probably tell me that it might be to my advantage to not use those as my limits, because you run into weird errors with sine and cosine if you do this. So what are you likely to do to ensure you don't run into errors with calculus? I'm hoping that somebody from a calculus class can tell me what I should probably do here. All right, I guess not. It sometimes happens where if you use a symmetrical integral like this, when you execute it, you will get a antiderivative that produces 0 for your answer when it's clearly not 0. Would you agree this product can't be 0? There's going to be a force on the charge. But with trig, you can sometimes be put in a position where you'll get a 0 for an answer. It's an issue with trig, and there's a name for this, and I forgot what the name is. But whenever you are going in a symmetrical, trigonometric fashion, like this, it's almost always more beneficial to remember this as a sum and go from 0 to one side and double it. It will save you for, I call them parity errors, but they're not really parity errors, and I don't know the name of what it's called. So it's almost always better to do it that way. We did that with the bar too. I want to remind you that this is still just a sum. You can do the sum however you want. Go ahead.
Do you also go from 0 to 1 radian?
Excuse me?
Do you go from 0 to 1 radian?
Why would I go to 1 radian? Because, 1 radian is somewhere before I reach the end of that arc. Right? Because the arc is like half of 3.14 radians. So it's like 1.6 radians. So I would stop too soon. Does that make sense?
Yeah.
Okay. All right, so can you finish this? How many of the room, I mean, I would hope that everybody who took mechanics last year and everybody's had calculus could finish this. Because we know what the antiderivative of cosine is. If you paid any attention last year, you know what the integral you know what the antiderivative of cosine is. And you guys from AP1, you don't. And I wouldn't expect you to be able to finish it. But this is not a physics topic, this is just a calculus topic. And I would really like to make sure we've at least executed one of these. So, first thing I'm going to do is bring down all of my constants. How you deal with an integral, and I'm really directing this to folks who have not had physics before, or calculus. We take this, which is our function, and find the antiderivative with respect to this variable. Now, the antiderivative of cosine is sine. It's not particularly hard. It's on your equation sheet that you'll get to. But that's the antiderivative. So I just write the antiderivative function here. Not quite done, but close to being done. We then bracket it with our limits. Now we're not done. We've done half of taking an integral. The first part of taking an integral is finding the antiderivative. The second part of taking an integral is what's called applying your boundaries, or putting in your limits. So to put in your limits, you put in the top limit first, subtract and put in the bottom limit. That's the second part of doing an integral. An integral has two parts. The antiderivative of the function you had yesterday was impossible for you guys to do in a reasonable amount of time. This one, stupid simple. So, what's sine of 0? Bye-bye. Sine of pi over 2? Not terrible, right? Now, had we left the original limits in, we would have gotten 1 minus negative 1, and it would have still worked out. We wouldn't have gotten an error. So we would have been okay. All right. Again, the physics ended right there. This was the calculus part. All right. But it's a ring of charge with a point charge located a perpendicular distance z away from the center of the ring. Tonight, I want you to just try to set it up. Spend 10 minutes.